In the last video, we discussed the definition of decision trees, how they can be interpreted, and how to use them for classification. In this video, we're going to talk about how to create them. One idea you might get is that we could just build all possible trees and evaluate how they perform on new data, or rather on training data. How can we build all possible trees? Well, we have to take a look at all possible splits. For that, we will take a look at these 8 data points right here. We will consider just one of their features, so that's why you can see them projected on the line. We have 8 data points right here, and there are 7 possibilities to split them in a way so that there isn't a region created which doesn't contain a data point. So a split right here or right here really doesn't make any sense. We can, however, use any value between 2 data points to create new regions. And it doesn't matter for the training set if the split is happening right here, right here, right here, or even on the exact value of a data point. It will separate the data points in the same 2 sets. Since our goal is generalization, it often makes sense, however, to split in the middle between 2 data points. Now we've seen that for these 8 points, if we just consider one feature, there are 7 possible splits. Usually our data doesn't have just one feature but more than one, so we have to consider all combination of features and values. For our simple example, where we have 300 data points, that means that we have to consider 2 times 299 possible thresholds. That is 598 possible tests at the root node, slightly fewer at the descendants, but still quite a few tests that we have to consider. Furthermore, the order in which we do those splits is important as well. Therefore, enumerating all possible trees is really just feasible for when we have a low number of possible tests. Otherwise, the number of trees quickly explodes, and finding the optimal tree is even NP complete. So what do we do instead? Well, we grow the tree top down, starting at the root, and choosing the best possible split, node by node, by using a greedy heuristic. And a greedy heuristic here means that we're not trying to find the overall optimal tree, but we're trying to do the best at our node that we're currently considering. One possibility is the misclassification rate at a node. The misclassification rate at a node T specifies the fraction of samples that would be misclassified if I treated node T as a leaf node. So that's just 1 minus the fraction of samples for the majority class. If we split a node T into 2 new nodes TR and TL by using split S, we can compute how much our misclassification rate improves. And this is done as follows. But let's take a look at an example. For the dataset that we can see right here, if we do not perform a split at all, we would get a misclassification rate of 1/2, because we classify all blue and all green points as red. If we split on x1 smaller or equal 5, then we get 2 nodes. One is a node that contains only red points, so its misclassification rate is 0. And another node that contains a third green points, which are misclassified because blue has a majority here. By performing the split, our misclassification rate should have improved by exactly 1/3, because all of those blue points right here are now correctly classified after the split. But let's check if our equation here gets to the same conclusion. So we have delta I for the node T is 1/2 minus 1/2 times 0, and 1/2 because we take exactly half of the points, minus 1/2 times 1/3. And that equals exactly the expected 1/3 improvement in misclassification rate. So the improvement in misclassification rate is one possible way to determine the goodness, so to say, of one split. Unfortunately, there are also some problems with that. And we can see that by looking at another example. Right here we just have 2 classes and 200 points. If we do not split at all, we classify the red points down here wrongly. So we have 40/200 samples that are misclassified. If we split on x1 smaller or equal 5, then we still misclassify those 40 samples wrongly because the 60 samples over here dominate the right side here. The same holds if we try to split on the second feature. There, in the lower part, it's also the green class that dominates. So even though we could use 2 splits to get to perfect classification, both of those would never be chosen because the improvement in misclassification rate by just 1 split is regarded as 0. And that's one drawback of using a greedy heuristic. So let's think about what else we could do. There are a few properties that we would like our splitting criterion to have. And these are these 3. We want it to be maximum if the classes are equally distributed in the node. So in the case of 2 classes, the worst case is kind of if we have half samples of one class and half of the other class. On the other hand, we want it to be minimum if we have a pure node where all the samples belong to one class. That's kind of our best case. We don't have to do anything with a pure node. Additionally, we want it to be symmetric. So we want to treat the 2 cases that look like this in exactly the same way. A function with these properties can then measure how pure the distribution at a node is. And ideally, we would like nodes to be as pure as possible. Some functions that have these 3 properties can be seen on the slide right here. Note that the misclassification rate, even though it has some drawbacks, still fulfills all the properties that we've talked about before. 2 functions that don't suffer from the same problems are entropy and the Gini index. You've heard a little bit about entropy before in the probability theory lecture, and we're going to take a closer look in the next couple of slides. And is originally related to estimating the inequality of income distribution in countries. But let's get back to entropy. And for this, we're going to take a detour into information theory, which is about encoding and transmitting information and doing so in an efficient manner. Let's say you have a friend at university who keeps you updated about what's happening today. So he sends you 1 of 4 messages every day. Either it says that you have a lecture, you have an exam, there's going to be free beer today, or nothing is happening. Each of those 4 messages occurs with a certain probability. And these are as follows. Yeah, it might be a little bit of wishful thinking that in 30% of the days there's going to be free beer, but you know, this is just an example. Now we want to encode these 4 messages in a way that on average we spend the least amount of bits possible. How do we do that? Well, we use a procedure called Huffman encoding, which assigns the shortest code, for example 0, to the message that occurs most often. The second code is 10 and gets assigned to the second most likely message, and so on. We are not using 1 as an encoding for the second most likely message because we want to figure out which message we receive when we get a long stream of data. So let's say we got a bunch of zeros and then a 1 and a 0, and so on. If we had both 1 and 1 0 as possible encodings for messages, then we would not be able to find out which message was sent. So this means that no encoding can be a prefix of another encoding. If we now calculate the average number of bits that we spend, the result is 1.36 bits. Now, why did we take a look at that? Because Shannon Entropy actually gives a lower bound on how many bits are needed on average to encode a certain message. We can see that Shannon Entropy is a weighted average of the minimum number of bits needed to encode a message by looking at its definition. It is defined over a discrete random variable x with possible values x1 through xn. The minimum number of bits needed to encode an outcome of a random variable is a logarithm of 1 over the probability that we have the outcome xi. And when we weigh this by the respective probability and use the laws for logarithm, this is exactly what we end up with. Shannon Entropy also measures the uncertainty about the outcome of x and gives us an idea about the information we gain when we observe x. If there is only one outcome with probability 1, then the entropy is 0, because we need 0 bits to encode that outcome. We are already certain that it's going to happen. If, on the other hand, we have 4 equally likely outcomes, for example, like when we have 2 consecutive coin tosses, then our entropy is going to be 2 bits. This is also the maximum value the entropy can take if we have 4 different outcomes for x. Now, with these functions that we just discussed, we can compare all possible feature tests and choose the one where the improvement is largest. For our toy data example, we will look at the Gini index to build the tree. Before having performed any split, we have 65 green, 67 red, and 168 blue data points. If we compute the Gini index for this, we have to subtract the squared fractions from 1, and the result is 0.589. A split on the second feature at value 3, we get these distributions right here. And you'll just have to believe me, the Gini indices for the left and the right node are 0.6548 and 0.3632. If we compute the difference weighted by the number of points that get sorted into these two nodes, we get the result that our improvement is around 0.07. Now we do this for all possible thresholds, and you can see the result right here. Over here we can see the Gini index if we split on the second feature, and over here we can see what happens when we split on the first feature. Now we want to choose the split where the Gini index is maximum, and for the first feature that happens somewhere around here. And you can see that it's around 0.05 maybe. For the second feature, the best value is right here. And we computed it on the previous slide. It was around 0.07. And the splitting value for this one is around 3. Since this is also the maximum of these two values, we would perform our first split somewhere around here. And this is how the decision boundaries look like after that first split. we have an accuracy on the whole data set of 58.3%. And you see that there are a lot of points that are misclassified. Now we continue to grow our tree using the exact same procedure by evaluating all the different thresholds that we can take. And at depth 2, the result looks like this, with accuracy 77%. At depth 3, the result is this, with 84.3%. This is depth 4. And if we do this until we have a maximally pure tree, the result would look like this. Maximally pure means that in each leaf node, there's only one class present, and each of the leaf nodes is pure. So we have an accuracy of 100%, but you can see with the stripes right here, or right here, or here, that we are clearly not generalizing very well anymore. What actually happens here is that we are overfitting our data, and that means that we are modeling our training data too closely and don't generalize as well anymore.